Hi everyone, so today we're going to talk about relative motion. So if you remember, I think it was probably the first lesson we talked about frames of reference. And all measurements we make are relative to a frame of reference, which is a way to say a specific point of view. So the best way to see what I mean by this is by example. So this is the same example I mentioned before. We're sitting on a train that's moving at 80 kilometers per hour, and a person on that train passes you up at a speed of 5 kilometers per hour. From your point of view, that person is moving 5 kilometers per hour. But if someone was standing outside the train and they look in, they would say that the person walking on the train is moving 85 kilometers per hour because they're moving at the speed of the train plus those 5 kilometers per hour. Both these statements are valid, they're just from different frames of reference, different point of views. So we're going to be studying relative velocity in particular. So let's say, for example, we've got the situation here on the right where we have Amy, Bill, and Carlos, and they're all watching the runner. So all these people are observing the runner, which is in the middle of the image. Amy looks at the runner, and Amy says the runner's velocity is 5 meters per second forward. Amy here, because she's on the ground, we actually call this the lab reference frame. So if she's moving at a relative speed of 0 with respect to the ground, this is called a lab frame. Now Bill, he has the same velocity as the runner. So when he looks over the runner doesn't really seem to be moving. Right? He doesn't know that there's the ground there. He doesn't notice the motion of the ground moving past the runner. From Bill's point of view, the runner is moving at 0 meters per second. Whereas Carlos is in the speeding car here, moving 15 meters per second. He says the runner's velocity is negative 10 meters per second. All these statements are correct. They're just with respect to different reference frames. Let's say we wanted to compute the velocity of the runner with respect to Carlos. Now the way we would do that is use an intermediate transition, so to speak. So, for example, here, if you skip down to the equation here, this is the velocity of the runner with respect to Carlos. So that's what these subscripts mean. Runner with respect to Carlos. We're trying to find the velocity of the runner with respect to Carlos. We know that the runner's velocity with respect to Amy, this term here, velocity with the subscript RA, so runner with respect to Amy, is 5 meters per second. We also know that the velocity of Carlos with respect to Amy is 15 meters per second. Right? Since Amy's still with respect to the ground, we could also have this instead of relative to Amy. The values would be numerically equivalent if we said with respect to the ground. Anyway, so going into that, when we add these terms, what we want to do is rearrange the subscripts so that a same letter is sandwiched in the middle, and those letters, in a sense, cancel out. And in doing so, we're going to properly add these velocities. So we want the velocity of the runner with respect to Carlos. So we want R on the left and C on the right. That's why we have RA here and AC here. The A's are going to cancel, so we don't have to worry about that. So here we can plug in the velocity of the runner with respect to Amy, which we have up here as 5 meters per second. Here we need the velocity of Amy with respect to Carlos. We have Carlos with respect to Amy saying that's 15 meters per second. That's equivalent as saying the velocity of Amy with respect to Carlos is negative 15 meters per second because they are going to be equal in magnitude, opposite in direction. So in doing so, we plug in our 5 meters per second, we subtract our 15 meters per second, and we get an answer of negative 10 meters per second. That is the velocity of the runner with respect to Carlos, which is what we saw on the page before. Right here. Let's apply this to some examples. So let's say we wanted to find the speed of a seabird, So researchers are doing satellite tracking of albatrosses and observed a bird maintaining sustained flight speeds of 35 meters per second. That's nearly 80 miles per hour. This seems surprisingly fast until you realize that this particular bird was flying with the wind, and the wind was moving at 23 meters per second. We want to see what the bird's airspeed is, its speed relative to the air. This will give us a more truer measure of the flight speed. So the first thing we do is draw a diagram. Your diagram does not have to be this elaborate, but here we have a bird moving. We're going to call our rightward direction as our positive direction, positive x in specific. So we can label the velocity of the bird with respect to the water. We were given that in the problem. The velocity of the bird with respect to the water is 35 meters per second. We can also label the velocity of the air with respect to the water, and that's 23 meters per second. So those are both givens in the problem statement. Just to let you guys know, if there's a B in the subscript, that represents bird, A represents air, and W represents water. We are looking for the speed of the bird with respect to the air. Right? That'll give us the truer meaning of how fast he's going. So we want our inner subscripts to sandwich together and cancel. So we have bird, air, and water. We don't want to deal with water in our answer, right? We want the velocity of the bird with respect to air. So we're going to use that W subscript to cancel. So since we want bird on the left, we're going to have the velocity of the bird with respect to the water. And since we want air on the right, we're going to have velocity of the water with respect to the air. Now, the velocity of the bird with the water, we have here, velocity of the bird with the water, and that's 35 meters per second. And we need to add the velocity of the water with respect to the air. In this case, the problem tells us the velocity of the air with respect to water. Water with respect to the air is just going to be the same magnitude, opposite in direction, so it's going to be a negative 23 meters per second. So when we plug in those values, we get that the velocity of the bird with respect to the air is going to be 12 meters per second. And this is about 25 miles per hour, which is pretty reasonable. And this answer makes sense. We got an answer that is slower than the speed we originally observed, so that's good. That's why this minus sign here is extremely important. If we had forgotten to flip the subscripts and flip our negative signs, we'd have gotten a larger number, which would not make sense for our situation. We also have situations in which we're going to be dealing with vectors. So we can also add vectors in the same sense. So let's say we're trying to find the ground speed of an airplane. So Cleveland is about 300 miles east of Chicago. A plane leaves Chicago flying due east at 500 miles per hour. The pilot forgot to check the weather and doesn't know that the wind is blowing to the south at 100 miles per hour. We want to find the plane's velocity relative to the ground. So let's diagram what's going on. So we have Chicago and Cleveland, and we can draw a velocity vector of the plane with respect to the air, and that's due east. And we can also draw a vector from our Cleveland, the velocity of the air with respect to the ground, and now is moving due south. So we have east to the right, south in our downwards direction in this diagram, right? So our known values are the velocity of the plane with respect to the air, 500 miles per hour east, and the air with respect to the ground, that's 100 miles per hour south. Excuse me. So now our velocity vector actually is going to be pointing from Chicago to the south of Cleveland, and it's going to be the resultant vector of the addition of these two vectors based on our situation. And that's going to tell us the velocity of the plane with respect to the ground. So since that is our goal to find the velocity of the plane with respect to the ground, we want to sandwich some intermediate variable. In this case, it's going to be the air, since we don't care about the velocity with respect to the air for our final answer. So that's going to be our sandwich variable, is the air. We want the plane on the left, and we want the ground on the right. So we're going to have the velocity of the plane with respect to the air added to the velocity of the air with respect to the ground. So since the plane's speed Our velocity relative to the ground is going to be the size of our resultant vector, the hypotenuse. So it's going to be the plane speed. It's going to be the magnitude of that vector. We can just use the Pythagorean theorem to calculate its speed. So using the Pythagorean theorem, we have the two base lengths here. We want to find the hypotenuse length. So we're going to square the velocity of the plane relative to the air and add that to the square of the velocity of the air relative to the ground and square root of that quantity. So plugging those numbers in, we get a value of 510 miles per hour. So the plane speed is going to be 510 miles per hour. But we're not done because it asks for the velocity. And the velocity of the vector has both speed and direction, magnitude and direction. So that's its speed. Another thing to note here, just notation before we move on, whenever we're writing down vectors, if it's typed, vectors are going to be in boldface, in bold font. If it's handwritten, vectors are going to be represented by drawing an arrow on top of the v, in this case, the velocity vector. But I digress. So we found the plane speed, or the magnitude of its velocity, not its velocity. So we need to specify a direction. So we do that by specifying an angle. So in this case, we'll label this angle here in our diagram and specify that angle. So we can use trig to calculate that angle, right? So here in this case, I decided to use the tangent function. Tangent's opposite of adjacent. So this could be this velocity here divided by this velocity arrow here, the magnitude of both. So that value divided by that value. And then because we're solving for angle, we do the inverse tangent or arctangent if that's the vocabulary you're used to. So that reduces to tangent inverse of 0.2, which gives us 11 degrees. Now when you're saying your answer, you have to be specific. So the plane's velocity relative to the ground is going to be 510 miles per hour, 11 degrees south of east. If we just said 11 degrees, that's ambiguous. We don't know how that 11 degrees is measured. We don't know if we're going clockwise, counterclockwise, anything like that. That's why we have to specify south of east in this situation. So just make sure in the future, if you're specifying an angle of a vector, you specify with what respect you're measuring that angle from. So one quick question for you guys. A factory conveyor belt rolls at 3 meters per second. A mouse sees a piece of cheese directly across the belt and heads straight for the cheese at 4 meters per second. What's the mouse's speed relative to the factory floor? So here's a diagram of the situation, so you guys don't have to diagram it necessarily, though you might want to draw an adaptive diagram. So pause this video, think about it, try to answer the video before you move on. So in this case, we're looking for the resultant vector again. So again, we're going to get a velocity vector. Though, what's nice is looking for speed, so we don't have to calculate the angle. So we just need to find the speed. Right? If you look on the previous slide here, it asks for the mouse's speed. So that means we don't have to do that extra step. To find speed, we just need to find the hypotenuse of this triangle. So the rat is moving 4 meters per second to the right. And then we've got the conveyor belt moving down at 3 meters per second. Using the Pythagorean theorem, or you could also just realize this is going to be a 3, 4, 5 triangle. That's the fastest way of looking at it. So since it's 3, 4, 5 triangle, our speed is going to be 5 meters per second. So one thing to note is just to be careful, make sure that your velocity vectors again sandwich. Since we're adding here the velocity of the mouse with respect to the belt, we want our next vector we add to be the belt with respect to the floor. So still make sure the B's are sandwiched together and canceled out. Right? If you needed to flip a vector, that's fine. Just make sure you draw your new diagram accordingly. Alright, thanks everyone.